In this video, we'll see ZCA preprocessing, which is a very useful preprocessing to apply to our data before we run a sparse coding algorithm. So sparse coding is trying to learn about the structure, the statistical structure of our input data. And we find in practice that it's often beneficial to remove part of the structure which is quote-unquote obvious. Which is not particularly interesting and would not allow us to extract interesting features. So for instance, the mean of the data is not something that's particularly interesting for representing our different data points into a feature vector, latent representation. And also some of the linear correlations, or the covariance essentially of our data, is also not a kind of statistical structure dependence that's particularly interesting. And so for that reason, what we often do in ZCA preprocessing is just remove the mean and also do preprocessing such that the empirical covariance of our data is going to be the identity, which will mean that the covariance between the preprocessed data between the elements of the vectors in the preprocessed data is going to be 0, and then the variance of each element in our preprocessed data is going to be 1. And so that's a process known as widening. And so in statistical jargon, we will say that by doing this, we'll remove the first and second order statistical structure in our data. And so it means that our sparse coding algorithm will then perhaps extract structure that's a bit more complicated in a higher order. And so ZCA preprocessing is very simple. I just described the procedure. So what we do is first we compute the empirical mean of our training data, as well as the empirical covariance matrix. So mu hat will be empirical mean, and sigma hat the empirical covariance matrix. And we also assume that we have computed a eigenvalue eigenvector decomposition of our matrix. So here the eigenvectors are the columns of the matrix U, and then here lambda has 0 on its off-diagonal terms. It's a square matrix with 0 on its off-diagonal terms, and the diagonal terms correspond to the eigenvalues that are sorted. And now ZCA is simply a linear transform that takes a given input and preprocesses it as follows. It takes the input, subtracts the empirical mean, and then multiply by this transformation here, which is similar to this one here. So the difference is only that the diagonal matrix in the middle is going to be lambda, where we've taken the diagonal terms, and then we've taken the exponential, so exponentiated it by minus 1/2. So in other words, the diagonal terms are going to be 1 over the square root of the diagonal terms of this lambda matrix here, so the eigenvalues of our empirical covariance matrix. Okay, so now let's see how this transformation actually removes the mean and also makes sure that the empirical covariance matrix is now the identity matrix. So first with the empirical mean. Now if we take the empirical mean of our preprocessed data, it means we take 1 over t times the sum over all of our training data of the transformed data. So xt minus the empirical mean multiplied by the transformation matrix. Now because this matrix here does not depend on t, and nor does the empirical mean, then I can put the sum right inside here. So I can have that this is equal to the linear transformation times the average of xt minus the empirical mean. And now the empirical mean is just the average of the xt, so this is just sigma, mu hat. And then so we have mu hat minus mu hat, which is 0, times this transformation, that's going to be 0. So we do have that the empirical mean is equal to 0 once we've performed this transformation. Now let's show that the empirical covariance matrix is also now the identity once we've done this preprocessing. So here's the expression for the empirical covariance matrix for our transformed data. So it's the outer product of the transformed data with itself. So normally you'd expect minus the empirical mean, but we've shown that it's 0, so we just have the outer products of the transform vectors. And now similarly, because this matrix here and u hat, this matrix here and u hat here does not depend on t, then I can take the sum and introduce it further into the expression. So I'll have 1 over t minus 1 times sum over t of these terms here, where xt depends on t. And so we have this expression. So essentially, I've been able to factor out that transformation here out and here out, and put the sum within here, right here. So I actually haven't had to use the fact that mu hat doesn't depend on t here. And now we notice that this is actually the empirical covariance matrix. So this is sigma hat. Now sigma hat in its eigenvalue decomposition is equal to this. And now, well, we have a bunch of terms that are going to cancel out. So first, because the eigenvectors are orthonormal, then if I take the a matrix U transpose, so U transpose, its rows are the eigenvectors times the matrix U whose columns are the eigenvectors, then that's going to be the identity. So 0 off diagonal and 1 on the diagonal, because the vectors are orthogonal and they're normalized. So this disappears. This disappears for the same reason. Now I have the so the inverse square root of the elements of lambda matrix times the lambda matrix. Well, it means that I can make that disappear and have just 1/2 here. Now I have lambda 1/2 times lambda minus 1/2. So again, this is going to cancel out. That's going to be the identity. So now I have U times U transpose, which is equivalent to the eigenvalue eigenvector. So if I have I essentially have in the middle right here, it's as if I had the identity. So I have U times the identity times U transpose, which can be understood as the a possible eigenvalue eigenvector decomposition of the identity matrix. And so that means that U times identity times U transpose is really just the identity matrix. Okay, so we've shown that if we take the covariance matrix, the empirical covariance matrix of the transform data with ZCA preprocessing, we get that now this covariance matrix is the identity. So the variance of all the elements in the transform vectors in our training set is 1, the empirical variance, and the covariance between each pair of different elements in these transform vectors is also 0. All right, so we've seen that ZCA preprocessing removes the mean and transforms our data so that the elements are linearly independent, so they're not linearly correlated. And if we do this, then empirically we find that if we, after perform this preprocessing, we run sparse coding, we tend to get a better feature representation of our data.